Yes, we'll record this in the, yes. Okay, my apologies for not, I went through and did, if you record, if I started and then just recorded a little bit late, we went through an example here to find that a representation of the identity is a basis change matrix. And then we started using it. And now we're pointing out that any invertible matrix, any matrix, invertible matrix, let me get this down so it's not, is a basis change matrix, which means that if I apply, when I'm applying Gauss's method, what I'm really doing is changing bases. And so we'll look at that a little bit later. What we want to see is, well, this changes vectors, and you've done that before. So this just sort of automates changing a vector from one basis to another, right? And you already know how to find, it's just like, it's interesting that this is a representation of the identity. This is another representation of the identity map, but it doesn't look like this. So, but it just works the way you can find, given any two bases, you can find the identity map that changes, but the matrix that changes bases from one basis to the other. Okay, but what about matrices themselves? For example, if I have a matrix M, the point is that I want to know okay, so here's the situation. Let's say I have vector space V and I have a map M between V and W, okay? And I want to find the representation of this map. So I could do two things. One is, and let's say I want to find basis, let's see. Let me just make sure I want to follow the same notation as the text. So what we've looked at here is this changing representations of vectors, and this is just repeating what we've just said about this result that every invertible matrix is a basis change matrix. There's some examples. Yeah, if a matrix is non-singular, it implements a change of basis. Okay, so that's all just proving those things. But then this is the section I wanted to go to, and here's the diagram I wanted. Okay, and so let me use the same notation just to sort of explain this diagram. So let's say what we have a vector with basis B1, and we have a map H with a representation H1 that goes to W and codomain basis D1. This is the usual picture we've worked with. If you're given a basis action here, you can find H1 from if given the formula here. We've given various things. Given the map, we can find H1. Given H1, we can find the map. Given the basis action, we can go back and forth between two bases. But what happens if there's a second way, which is, let's say we have a second basis for V. Well, there's an identity map that takes V from B1 to B0. And we can also take W with its map W and then sort of see, well, I can map this way. So that between V and W, I have the same map, but a different representation, because this is the representation between B1 and D1. This is the representation, H0 is the representation of H between the same vector spaces with different bases, right? So each representation has a pair of bases. This one has the domain basis B1, the codomain basis D1. H0 has domain basis B0, codomain basis D0, right? Well, I can calculate H1 in two ways. One is just directly the way we've done it. The other is I can take a vector here, transform the vector to this, go to this basis here, implement the same map. This is the identity map between V and V. This is the identity between W and W. And then if I know, let's say I know H0, then I can see that H0 and H1 are both representations of H, but so this is what we want. We want to see, we can calculate H1 by going from I to V, from V to W, from W to I, like that. Okay? So, so if we start, we can sort of see that H1, this goes from B1 D1, acts on vector V that's in B1 and produces a vector W that's in D1. But I could also start from vector B1, have act with I, B1 to B0. That changes it to the B's. This is the same vector, but in the B0 representation. Then act with H0, which goes from B0 to B1, and I get over there, and then I can come with the identity from D0 to D1, and I should get back to WD1, because it's one map. It should go to the same thing. Well, it turns out, because this should work for any vectors here, these two patterns have to be the same. What I'm trying to explain is why H1 that goes from B1, D1 can also be calculated by D0, D1, H0 from B0 to B1, and then I from B1 to B0. So basically I transform this matrix by acting with a basis change matrix, a representation of the identity on either side. Okay? So that's the one task here is. Now, why is this okay. So let's go through, maybe the point is to do, so the whole point of this is sort of, we want to understand concretely how to do this and then apply it to Gauss's method. Let me show you the application, what the point of this is. What Gauss's method, a linear system is given by a map and a target vector in the range space. So I have a representation of that map, and it takes a vector V in the domain and gives it to some target vector I've chosen in the codomain, right? Well, when I perform Gauss's method, I act with, say, a row operation, an elementary matrix, right, that implements a row operation on M, but I also perform that row operation on the target vector, right? So when I use the augmented matrix, I do the row operations on both M and this vector at the same time, right? So what I'm starting with my vector system here, and I'm performing the row operation matrix on both sides. So if this equation is true, I've just multiplied both sides by the matrix R1. Well, R1's an invertible matrix that changes bases. Well, if I write M here, the columns of M span the range space. So if I write this as, let's say it's three-dimensional, x beta 1 plus y beta 2. Well, these are the columns of M, and I'm acting with R on those things which maps V to R on W, then I can think of this matrix R as acting on beta 1, acting on beta 2, acting on beta, because I can multiply this in to get X R beta 1 plus Y times R beta 2 plus Z times R beta 3. And that whole thing maps V to R WT. Now, what's going on here? What's going on is that this changes beta 1 to a new basis. This changes beta 2 to the same basis. This changes beta 3 to a new basis. These are the bases in the codomain. So what Gauss's method is doing, and this changes the target vector to the same basis. So what's saying is I'm changing bases in the codomain to make it clear that what's linear, which of these vectors is linearly independent. The column, when I get to echelon form here, say, like this column and this column when I get to echelon form, this column and this column form a basis for range space, because you can see this one is linearly dependent on the first vector, and this first term here is linearly dependent on this, and this one on this. So this is linearly dependent on this one. Now, I can't, with row operations, get rid of these and make the final change to a basis. But when I go to reduced row echelon form here, what that final one for this matrix would do is would give me 1, 0, 0, 0, 1, 0, and then 1, 1, 0. So what happens is then that this one is a standard basis vector. This one is a standard basis vector. So the Gauss-Jordan procedure, what it's doing is producing a standard basis for the range space, which then you can just read off, because you can see this vector is linearly dependent on this one. This one is linearly dependent on these two. Excuse me? Between here and here, this is echelon form. This is reduced echelon form. See, I got rid of just this one here because this was a leading variable. So I had to add maybe make this 2, and so then I'd get one. Then I'd subtract this here, and I get 1 here. Okay, I just want to have a general case so that now it could be this has gotten rid of. The point is that everything else is manifestly linearly independent. So I can just easily see how to form a basis for range space. And these ones here give you dependence on null vectors, right? But then, okay, so this is what Gauss's method is doing, and the Gauss-Jordan method is doing. But it's not the complete story. For example, one thing I could do, see over here, when I went up here for this same, I can change this on both sides, right? I can change the target vector over here with both sides, and I haven't done that in the linear system. So here's the final step, which is, it turns out that an elementary matrix, so here's the point, an elementary matrix which acts from the right rather than the left, okay? implements column operations. Okay, so what does, so here's an elementary matrix that rescales row 2. You know, it does 2, row 2, right? Well, if I take an arbitrary matrix and multiply that matrix by from the right, rather than if I multiply it from the left, it's going to multiply the second row by 2. But if I multiply it from the right, I claim it's going to multiply the second column by 2, right? So it implements column operations. So if I do this first one here, if I just say this 1 times 1, right, is going to give me 1 times 1 plus 2 times 0 times 3 times 0 will give me a 1. But this first row times the second row is going to be 1 times 0 plus 2 times 2 is 2 times 2. And the third one will be 1 times 0 plus 2 times 0 plus 3 times 1 will be 3. So I've reproduced the first row, but with this intermediate one multiplied by 2. If I take it on the second row here, I'll get a 4. This 5 will be multiplied. And then 4, 5, 6 times this one will pick up the 6. 7, 8, 9 will pick up the 7. The 2 here will be 2 times 8. And the last one will be 9. So if I do matrix multiplication, I end up with the second column being multiplied. Okay, well, I can go and look at the row swap operation and see how that works. And that also works in an easy way. Like if I swap rows 2 and 3, and I multiply it from the right, it's going to swap columns 2 and 3, right? Because if I go through here, I can see this row times this one's going to produce a 1, but this row times this one is going to produce a 3, right? Because it's 1 times 0 plus 2 times 0 plus 3 times 1. And the last one is 1 times 0 plus 2 times 1. So I've swapped the first two. Then the second row times the same thing is going to give me a 4. Then here I'll pick up the 6, right? Then the last one here, I'll pick up the 2. And I've gotten the 6 and the 5 rather than the 5 and the 6. The last one will give me 7. Then 7 times 0 plus 8 times 0 plus 9 times 1. And the last column, 7 times 0, 8 times 1. So I've swapped the columns, okay? And now you can also think of this as, when I did the row operations, I took the identity matrix and implemented the row operation on that matrix. So if I do the same mnemonically, if I want to multiply the second column, I implement that column operation on the second column, I get this matrix. If I want to swap 2 columns, and I start with the identity matrix and I swap the columns 2 and 3, I get this matrix. Now, the same thing does not happen with row combination operations. If I want to do, say, row 1 plus row 2, well, what would I do? I would start with the identity matrix, right? And add row 1 to row 2 to get this matrix, right? But look, if I was to say, what do I do to get this from the say this one is row 1 plus row 2, right? But if I acted on columns, this would be row 2 adding row 2 to row 1 to get this. It's sort of like the rows go down here, but the columns go down here. So K times row I plus row j as a row goes to what I'm going to do over here in the column kappa. It's going to be, well, let me call this R. Would go to R kappa j plus kappa I, right? So we're going to do the row operation here, but we're going to say this is the column operation. You add column 2 to column 1, make that the new column 1. So if I added 2 to column j, so these two are the same matrix. So they change a little bit, but it works, okay? So in Gauss's method, we haven't done that. And I sort of dissuaded you from doing that. But what we could do in Gauss's method is the following. We have R M V equals R W. And we could take for R a sequence of elementary row operations which changes basis to the final one, which produces echelon form, right? So this matrix could go all the way and produce echelon form. But the matrix we get from reduced and even reduced echelon form, the matrix we get still has dependencies, right? So what we can do is we can act with say a matrix S here. This is my new, this is my sort of in the reduced echelon form basis. This is the reduced echelon form basis. I took S inverse here, so it changes the domain basis, right? So this is the matrix here that I've changed the basis of the domain and the codomain. So it's the same linear system. So this sort of gives me an extended Gauss's method where I not only change the codomain basis, I also change the domain basis. And then it turns out that all of the matrices like this, all are of one form. If I choose this properly, what you can do is up here, you can see from this reduced form, I could add minus column 1 to column 2 to get rid of that 0. I could add minus column 1 to column 4 to get that one, and minus column 3 to 4 to get that one. And then I could swap rows 2 and 3. So all matrices, any matrix can be brought to what's called block diagonal form, which looks like this, right? There's only ones on the line. It doesn't have to be square. I just written this. There have to be ones along the diagonal. There could be zeros, right? And I can always make this. So this basically, I can form a maximal standard basis for. So the matrix just acts like this. This is the null. So on any vector x, y, z, w, it's going to go to the target vector, like 1, 2, 3, 4, right? And what's going to happen is, so this is if I change these bases, this is if I have any matrix that has well, this one would be codomain basis 4, domain basis 4, and rank equals to 3, right? And then it's going to have nullity 1 because it's going to have one free variable here. Well, the action of that any linear system can be brought to this form. So any linear system that has dimension d for the domain and rank 3 and some rank will have a block form like this. I can solve it right away just by saying, well, x equals 1, y equals 2, z equals 3, and this last one would be, well, I need to have a 0 over here. If it either has no solution or if it's a 0, then I'm going to have 0 equals 0. And then so the null space then would be 0, 0, 0, w, the null space. be all these, and the range space would be all the other vectors here, and you have a solution. So the solution is just this vector here. So you can just then read off the solution and then apply some basis change matrices to get it back to the original form if you want it. So you can, it's not practical because you usually want to be in this original basis. So it's not practical, but you can see that all linear systems are classified by two numbers. Well, by three numbers: the dimension of the domain, the dimension of the codomain, and by the rank of the matrix. And if you get those three numbers, any linear system can be brought to this block diagonal form. Every map is if you change bases appropriately, is just block diagonal. So it's a special matrix, a special basis in which the map and the matrix are utterly simple. They're as close to being the identity matrix as possible. Now, this sort of seems like it reduces all maps to nothing, but let's say that I had a map, linear map, that rotates vectors, right? By an angle theta. All this theorem says is, well, I can find another basis here that's rotated by 45 degrees, x, y, x prime, y prime. So I have this basis, I have this basis. In this basis, if I rotate by, say, a given by 45 degrees or by theta, and I'm doing it from basis, the original basis to this basis, it will just take like 2, 0 will go to 2, 0 because all the complexity of the rotation is in the basis change. That's all it's saying. It's saying that I can find a basis in which the map acts as like almost the identity. That's all. So that's the whole point of this chapter, is to sort of give you a picture of what's going on with Gauss's method and how it continues, like with that. Okay, so what tasks do you need to do? Well, the new thing you want to do is find representations of the identity matrix, which you can already do. Is simpler than before. The other is to change a matrix from one basis to the other. So let's say that you had the map H from, say, x, y to x plus y, x minus y. So it's R2 to R2, right? Maybe we should do R3, just so it's not square. And then we have, say, just x. Okay. So now H is from HX from R2 to R3. Well, what's the matrix H if we choose here? Let's first choose, let's choose the standard basis here and the standard basis here, right? Then what's H? From standard basis to standard basis. Well, we know that we do is we look for the images of the standard basis vectors. For 1, this would just be 1, 1, 1, because x is 1, right? And y is 0, and then 0, 1. For y is 1 would be 1 minus 1, 0. So H here is going to equal 1, 1, 1, 1 minus 1, 0. So now, let's say that we want to use 1, 1, 1 minus 1 for the domain. And for the codomain, let's use 1, 0, 0, 1, 1, 0, and 1, 1, 1. Okay? Then the problem is, what is HBC, right? Well, we could go through and just say, well, we know what H is. Let's go and do what I told you before is, well, you take this vector, right? And you would take the images of these vectors and then transform them to C here, right? So, but we know that there's a connection between these two matrices, that which should be that if I have what I know is this one here. But if I go up here to V and B, B and C, and oh, let's do it the other way around. What I know is H standard, and I want B, C. So H, B, C equals identity VX, identity that goes from V to the standard basis up here, but then acts with standard to standard to get over here, and then comes here the identity from standard to C. So it starts from B, goes to E, E to E to E, then E to C. So I can calculate HBC by calculating, I already know this from up here, but I want to see that I can calculate these two. Well, this is also W. This isn't the same space, so these are a little bit different. Okay, so we need the identity matrices from E to C and B to E. Well, E to C is from V. So what's the identity matrix from the standard basis to, and we're going to this basis, which we have already done. What's the, well, we know that from E to, we want to go from, but we want to go, we want the other way around. We want not E to B, we want I from B to E, right? That's the inverse map. We can treat that as the inverse, or we can just say, what is the image of 1, 1, right? Which goes to the same vector 1, 1, which equals 1 times 1, 0, plus 1 times 0, 1, right? So it equals 1, 1 in this basis. So this is already, in the standard basis, because we've been given, in some sense, we've been given 1, 1 in the standard basis. So it is 1, 1. It's a little bit confusing because, see, I've given you these bases in this. So this is it, right? Because we're in the standard basis. Then I want 1 minus 1 goes here to 1 minus 1. So I VE equals 1, 1, 1 minus 1. And that's this one here. And that's going to be this one here. It's going to act on the right, because we can act with this one on the right with that one. Then we need E. We need the other one that goes between from the standard basis to this one. So we need the identity map from 1, 0, 0, 0, 1, 0, 0, 0, 1, 2, 1, 0, 0, 1, 1, 0, 1, 1, 1. Okay. Well, is going to go to the identity map, which in this basis is, this is in standard basis, this is in C, this is it in C, and then we want 0, 1, 0, goes to 0, 1, 0, and we need that in this basis here. Right? And you can see that you're going to need T equals 0 because we only need these first two. And we need S equals 1 to get that one. And so we need R equals -1 to cancel off that. So this one equals -1, 1, 0 in basis C. The last one, which we might just get in here before the end of the class, is, well, R100 plus S110 plus T111. Well, here you can see because of this one, we're going to need T equals 1 because they can't be played off against other ones. Then I have to play, since T is 1, S has to equal -1 to cancel off these. But if S is -1, I'm going to have 1, -1, so R is 0. So this one's going to equal 0, -1, 1. So the identity map from the standard basis to C is going to equal 1, 0, 0, -1, 1, 0, and 0, -1, 1, as long as I haven't made any mistakes. Then my final matrix HBC should equal this matrix 1, 0, 0. At least I can write it out. -1, 1, 0, 0, -1, 1 times the H, one, 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 -1, 0 times the basis change matrix. The other one, which I think is this one, 1, 1, 1, -1. So if I carry out this multiplication, I'm going to get HBC. Okay, so it's tedious, right? But so it's like a big, it's like one. So it's not, and so basically that's the one kind of problem that I think there's one of these on one of the next, like homework assignment 6 is one of the, or maybe, yeah, one of these in homework assignment 6. It's 12:51. I have a dentist appointment at 2 o'clock today, so I won't be able to have office hours at 1:30. But if I get finished, I will see if I can have office hours like from 3 to 4 or something in case anyone needs help with their homework that's due tonight, like 5-1 and 4-2, right? I mean, 4-2 if you need it. Okay, and I'll put the